Welcome to qnawire.
Hi, so for this problem, the way to find the pH is that we're going to employ the Henderson-Hasselbalch equation, which tells us that pH is equal to pK plus logarithm of the concentration of the conjugate base. In this case, this is going to be the concentration of the benzoate anion divided by the concentration of benzoic acid. To simplify it a little bit, I'm going to abbreviate the benzoate instead of being benzoate completely. Benzoate is going to become B minus just for a shorthand notation, and benzoic acid it is going to be directly HB. So first information that we need to get is the pKa, that is equal to minus the logarithm of Ka. This is going to give us a value of 4.2. The other information that we have of our system is that both of the benzoic acid and the sodium benzoate have a zero point 0.1 molar concentration. That means that in 200 milliliters, that is equal to zero point 0.2 liters, we're going to have an amount of mole of 0.02 moles of each of them. So this is equal to the amount of mole of the benzoate anion, and is also equal to the amount of mole of the benzoic acid that I have in the solution. So the next thing that is going to happen is that I'm going to add up 5 milliliters of a zero point 0.1 molar solution of HBr, which is a strong acid. This strong acid can react with my benzoate anion, with my B minus, right? So the amount of acid that I'm adding, remember that this is a monoprotic acid, so per each mole of HBr added is equal to 1 mole of hydrogen ion produced. This is going to be equal to volume in liters. That's why we multiply directly the milliliters by 10 to the minus 3 times zero point 0.1. So the amount of mole that we are adding here is 5 times 10 to the minus 4 mole of H3O plus. So with this information, we can look at the reaction of benzoate plus H3O plus in order to generate benzoic acid plus water. So for this, we need to look at our always reliable ice table. And in this case, the ice table is going to be written in moles. Okay? So initially, for B minus, we have 0.02. For benzoic acid, we have 0.02 as well. And we are going to add 5 times 10 to the minus 4 of acid to our solution. So the acid is going to be my limiting reagent. And the amount of change is going to be equal to the amount of mole of the acid that is going to react. So this is going to be 0.02 minus 5 times 10 to the minus 4, which is 0.0195. Here I'm going to have something close to 0. And of HB, 0.02 plus 5 times 10 to the minus 4, so 0.0205. And recall that both of these guys are moles. Now, after doing this, we could go ahead and calculate the concentration, because the total volume that we're going to get is going to be 200 milliliters plus 5 milliliters, which is 205 milliliters, equal to 0.205 liters of solution, correct? But that is not necessary in this case, and we would have to do an extra calculation. Why is that? Because if we take the concentration of B minus and divide it by the concentration of benzoic acid, remember benzoate and benzoic acid, this is going to be equal to amount of mole of benzoate divided by the total volume divided by the amount of mole of the acid divided by the total volume. Total volumes are going to cancel out, so we get amount of mole of benzoate divided by the amount of mole of benzoic acid. Luckily for us, we can calculate this directly. This is 0.0195 divided by 0.0205. So our result is going to be 0.95122. Okay? And this is going to be an adimensional number. So we can turn back into our Henderson-Hasselbalch equation. I'm going to rewrite it here just for sake of clarity. And we're going to replace the values that we found. So pH is equal the pKa that we calculated over here, that is 4.2. 4.2 plus the logarithm of this number, the number that we just calculated, 0.95122. The result that we get is going to be a pH of 4.178. If you want to go all the way to 1783, might as well. Or you can round it up as 4.18. And that would be all for this problem. Thank you very much.